Now let's look at the counting semaphores. The counting semaphore will be a structure like this. Watch it. Struct semaphore. It will have an integer value, right? And then it will have a queue. So what is this integer value means? Every semaphore, especially the counting semaphore, will have some integer value. It means that how many processes can enter into the critical section at the same time. That is called that is the meaning of this integer value. So semaphore is going to have initially some value. That value will determine how many processes can simultaneously get into the critical section. Some critical sections might allow more processes to get into this. For example, if you have 4 instances of a printer, then at any time 4 processes can access the printers at the same time. Why? They have four instances, right? So like that, if a resource is allowed to be shared by some particular number of by some n number of processes, but not more than that, then always you can go with the counting semaphores. So at any time, if value of the semaphore is positive, it means that these many processes can enter into the critical section. And in case if the value of the semaphore is negative, then it means that you cannot already some processes are blocked based on that value. Okay, I'll just tell you what that means. I'll just tell you, don't worry. And next one is queue. There is a queue which is called L. So L means this. L will contain set of all processes which are blocked whenever they try to enter the critical section because they didn't get the permission. Okay, I don't know if you understood this or not. Okay, let me take an example. I'll just explain you with this example. Watch it. Assume that we have a critical section and we have the entry code here and we have the exit here. Fine. Now our critical section is in such a way that at any time 3 processes can enter the critical section, right? Then what I do is I'll have a counting semaphore in the entry section in such a way that counting semaphore is initialized to 3, right? And whenever any process tries to enter the critical section, it will try to decrement it and then enter it. So let us say P0 has first come and it wants to enter the critical section. Then what P0 will do is it will decrement it. Now the value of counting semaphore is 2. It means that P0 has made the value as 2 and still it is a positive number, so P0 will enter it. So how many more processes can enter now? 2 more processes. Let us say P1 has come. Now P1 has P1 also wants to enter the critical section. Then it will decrement it to 1 and still it is greater than 0, right? Therefore it will also enter it, P1. And now let us say P2, the next process has come for execution and it will make it as 0, right? And still it is not less than 0, therefore it will also enter it. So P0, P2 and P1, all the 3 are simultaneously inside the critical section, right, or simultaneously executing the critical section. And now the semaphore value has become 0, right? And if any new process comes, let us say P3, and if it tries to enter the critical section, then what happens is the value of this will now become -1. We are decrementing it each time, right? Then what happens with this value of what does it indicate is it is not supposed to enter the critical section, and moreover this particular process will be added to the list of waiting process will contain P3. Now if P4 comes, then what happens is again it will be decremented and its value will be -2, right? And therefore again it will be added to the list, right? So if the value is negative for a semaphore, these values indicate -2 indicates that 2 processes are waiting for the have tried to enter the critical section but failed, and so they are waiting in the queue, right? They are blocked. So these negative values indicate how many processes are blocked, and the positive value indicates how many processes can enter into the critical section, right? And this is applied only for the this counting semaphore. Counting semaphore can take both the values, positive values or 0 or negative values. Whenever it is positive, it means that even more process can enter. The positive number indicates how many process can enter the critical section, and 0 indicates no more process can enter the critical section. In case if any process tries to enter, it is going to get blocked, and negative number indicates how many process have got blocked when they try to enter the critical section. Therefore that is how you could interpret these numbers of a counting semaphore. Now what happens is, in the exit section, whenever any process comes out, let us say the process P0 comes out, so whenever it comes out, it is going to increment the value of this. So after incrementing the value, its value will be -1. So whenever it is less than 0, it will understand that, oh, some processes are already in the queue waiting, which have got blocked, and therefore it will go and wake them up, right? It is going to wake them. So P3 will get unblocked. So P3 will get unblocked, and P3 can get into the critical section, right? So any process which tries to get inside the critical section should decrement the value of semaphore, and if the value of semaphore is less than 0, it should go and sleep in the list. It should sleep and then put its number in the list. And any process which tries to get out of the critical section should increment the semaphore value, and in case if the semaphore value is less than 0, then it can understand that, oh, some processes are less than or equal to 0, then it can understand that some processes are already in the waiting list, and it is supposed to awake one of the process and then get out of the list. So that is how we are going to use this counting semaphores. Therefore, counting semaphores should have some integer value, positive or negative, indicates how many processes can get into it and how many processes are blocked. And second thing is, you should have a list which contains how many processes are already blocked, right? And then next operations are, whenever they try to enter, we should have some facility using which they could decrement the value of semaphore, right? And now that decrementing should be in a atomic fashion, atomic way. Atomicity means when one process is trying to decrement the value of the semaphore, at the same time some other process should not do it, otherwise there will be inconsistency, isn't it? Therefore, we want some functions which are going to be implemented atomically at the kernel, right? Those functions are nothing but, here we need decrementing and here we need incrementing, and while decrementing we should check what is the new value, and depending on which we should know whether to allow a process inside it or whether to block it there, right? And while incrementing the value, we should check whether there are already some process waiting, can we let them inside, or we can directly come out. So one more thing is, in this case, we don't want mutual exclusion. It is not actually mutual exclusion, isn't it? When these many processes are present in the critical section, it is not actually mutual exclusion. In case if you want mutual exclusion, then set this initial value of semaphore as 1. So whenever initial value of semaphore is 1, only one process will be allowed to get into the critical section, and all the other process which will try to get into the critical section while one process is inside will all get blocked, right? And later what we do is, all those blocked processes will be in the list and they can be woken up one by one and they can be added into the critical section. And one more thing, the way if you use a queue here, that is always better. The reason is, if P3, P4, P5 got blocked in this order, then they will be woken up in that order, so that even bounded waiting can be guaranteed, which means the order in which the process get blocked, you are going to unblock them in the same order. Therefore, no process will wait forever. So bounded waiting will be guaranteed. In case if you want mutual exclusion, that will be guaranteed, and then progress will also be guaranteed, because if no one is going to enter this critical section, then anyone who wants it can enter it, isn't it? So mutual exclusion is guaranteed in case if you set the value of semaphore as 1. In counting semaphores, we generally have value of semaphore greater than 1, which means we don't really want mutual exclusion. But in case if you want mutual exclusion, then you can set the semaphore value as something as 1, and therefore mutual exclusion is guaranteed, progress is guaranteed, and even bounded waiting is there. Bounded waiting in the sense, you understood this, right? The order in which the process get blocked, they get unblocked in the same way, because they are all going to be added to the queue, and queue is a first in first out. So anything which got blocked first will get unblocked first, right? And but then everything, if you want to implement this, you need the support from operating system. Operating system should provide you with this atomic operations for decrementing the value and incrementing the value, right? And generally this decrementing and incrementing, these have some specific names. So when they were first used by Dijkstra, okay, watch it. So we want to decrement the value or increment the value, right? So here I am going to use decrementing is as down and incrementing as up. But then when Dijkstra implemented them in his research paper in 1965, he has used the letters for decrementing. I think he used P, and for incrementing he used V. These symbols he used, right? And some people will use for decrementing, they will say wait, and for incrementing they will say signal. Anyway, whatever they are using, these are the standard terminology: down, up, PV, wait, signal. Here I am using down and up. Anyway, in the exam they will clearly say what is that they mean by saying these symbols. Okay, let's see this. Now watch this one. I think I made the example clear. Now let's watch this one. So you understood this, right? Structure contains some integer value which will take positive or negative or 0. Positive values indicate that these many processes can be allowed, and negative values indicate that these many processes are blocked, right? And Q contains the number of all the PCBs. This PCB is nothing, you know that, right? Process control block, the entire information about a process. This Q contains what are all the processes which are blocked and waiting in the blocked state, and what is their information, so that you can wake them up. And now down, watch it. So down is like this: s dot value equal to s dot value minus 1. So whenever you want to perform the down on a semaphore, we are simply decrementing the value, right? And then if s dot value is less than 0, so it means that in case if you want when you try to decrement it, and if it is going less than 0, it means that the earlier value is already 0 or some negative value. Then you don't have any permission to enter it. I think I told you this. See this? See here, assume that initial value of the semaphore is 4, then P0 has entered, then it's okay, let's say 3 only. I already told you this. P0 has entered, its value will become 2, and P1 has entered, its value become 1, and P2 has entered and its value will become 0. Since the value is 3, only 3 processes can enter, and all the other processes are supposed to get blocked. See, since the value is 3, only 3 processes have entered. Now the value is 0. Now if P3 tries to enter, then what happens is it will decrease the value as it decremented the value, and now the value got less than 0, isn't it? Now the value becomes, after decrementing, it is minus 1. Therefore now the value is this. So whenever it is less than 0, then put the process PCB in list, which means you put that inside the list here somewhere, L, in the list L, you put that I am waiting. The process is P3, and you go and sleep happily in the block state, and later someone will wake you up. That is the meaning of it. Got it? Now the value is minus 1. It means that if the value is minus 1, it means that one process is sleeping, right? That is how down is implemented. Now let's look at up. So up means generally when will down be implemented is whenever any process is trying to get inside the critical section, it is supposed to apply down, and whenever any process is trying to come out of critical section, it is supposed to apply up. Now let's see what happens if I apply up. If I apply up, it is up UP, right? Let us say P0 wants to come out of the critical section. Then what it will do is, P0 is trying to come out of the critical section. What it will do is, it will increment the s dot value. Now if it increments the s dot value, the new value becomes 0. If s dot value is less than or equal to 0, which means after incrementing the value of s, if it is less than or equal to 0, then what do you think will be its value before incrementing? Definitely a negative number, which means definitely some process is blocked in the blocked state and is waiting for someone to come out. Just think about it, is logical. See, now I incremented the value, and after incrementing the value, if the value is negative, then definitely before incrementing it, it is negative. Then what does negative value mean? It means that some processes are waiting, isn't it? Therefore, in that case, which means if s dot value is less than 0, which means some process is already waiting. I don't know how many, at least one process will be waiting, right? And now select a process from L. So it is better that you select them in, first out, so that progress will be, bounded waiting will be implemented. Or it is not a rule. You can select any process, that is up to you. If many processes are waiting, you choose one of them, right? Select a process and wake up. Wake up means put it in the ready queue. Sleep means put it in the blocked queue. Wake up means put it in the ready queue, so that next time it will run and will get a chance to enter the critical section, right? So that is how this is going to done. In case if it is not less than 0, then it simply we increment it and we leave. Nothing is required. Got it? See this. Next time what happens? Watch it. Let us say P1 comes out. So when P1 comes out, it is going to increment 0 by 1, which means it will be now 1, right? What does it mean? Watch it. S dot value equal to S dot value plus 1, but S dot value new value is not less than or equal to 1. It is now actually, sorry, not less than or equal to 0. It is greater than 0. If the value is greater than 0 after incrementing by 1, then what could be its value before incrementing? Either it could be 0 or some positive value, which means there is no process which is waiting. That is why we don't do anything. Got it? So only when the value is less than or equal to 0, we try to do something like pulling out a process and then scheduling it. Otherwise, we just leave it as it is. Now, what is the new value for this? 1. What does it mean? Next time one process can enter without getting blocked. Got it? In fact, I think two processes can enter here, isn't it? No, one process can enter by already P3 is unblocked. Okay, anyway, we shall see with the examples what happens with all this decrementing and incrementing. Here my intention is to just show you how the code works. We can take some examples and see this. So it is important that you even remember these names. One is down, other is up, P, V, wait, signal. These are the most common terminologies which are used by various authors right from the beginning. So in GATE exam, sometimes they might not even say what does P and V mean. Actually, they are supposed to say it, but then I have seen some questions where they didn't mention it, which means you are supposed to know about it. So just by heart this terminology, down, P, and anyway we are going to see a lot of questions. It will be clear for you. Okay.